In this video, we're going to look into the N-dihedral group, the question that has been asked from you in our WhatsApp group, right? So before we go into that, let us recap on what we have been introduced in this section for some of the important definitions. For example, some definition of order. Okay, definition of order is given there, and then definition of permutation of a set. Okay, permutation of a set. So remember, permutation is a function. It is a function. And then before you can you are introduced with permutation group, right? What is permutation group? Okay, we're going to look into permutation group again in section 8. Okay, in section 8, in groups of permutations, right? Okay, this is the brief what permutation group is. Okay, example of permutation groups is also given there. Okay, and then a collection of all permutations will form a group. Okay, under the operation of permutation multiplication, the identity is denoted by iota there. Okay, by iota. What else? We also being introduced with this group, and we denote it as and we named it as a symmetric group on n letters. Okay, we denote it by Sn, right? Another definition is on cycles. Okay, what is a cycle? Okay, it's defined here, and then what is a k-cycle? Also defined there. What is the definition of transposition? Any cycle of size 2. And then cycle that are disjoint. Okay, so these are all important definition that you need to master. Okay, and then you are given example to check about your understanding on this definitions, right? And then some more example. Okay, so and then the dihedral group. Okay, it's the where the student has a lot of problems to understand. Okay, so we're going to focus on this one in this video. So we want to define the collection of finite group, okay, based on the symmetries on regular n-gons, okay, n-gon or polygon of degree n. Okay, so we use standard regular n-gon, okay, the one whose points are the nth root of unity. Okay, the nth root of unity, and then recall that nth root of unity includes all points. Okay, and then the first point is always the point 1, 0. So recall back from your nth root of unity, you always start the point by if this is your imaginary axis, this is your real axis. Okay, you always start at 1, 0 as your first point. Okay, and then the other points are uniformly spaced around the unit circle to form vertices of the regular n-gon. Okay, and then we denote these points. Okay, we denote these vertices by Pn. Okay, and then we label the starting point at 1, 0 with 0. Okay, and then continue labeling them with 1, 2, 3 until n minus 1. Okay, that's how we denote the Pn and how we label it, right? So around the circle of and then counterclockwise, looking at counterclockwise, and then this is the same as relabeling the isomorphism between nth root of unity and integer modulo n that we've seen in again in section 3. Okay, and then we refer to a vertex. We will reference it by its label. Okay, so the vertex 0 is the point 1, 0. Okay, and then so on and so on. Okay, so for example, for this triangle, then this trigon, so you can imagine as the center of your axis in that center. Okay, so this is your point 1, 0 like that. Okay, likewise for this a square, so your axis, if you look at based on what you've seen in section 3. This is your origin, this is your point 1 0. Okay, and the rest are the points as stated in the paragraph up there. All right. Okay, I'm going to take the annotation off because we are looking into the definition of dihedral group, the n-dihedral group. We start by n greater or equal to 3. So the n-dihedral group is the set of all one-to-one functions, okay, or one-to-one functions, phi mapping integer modulo n into integer modulo n that map onto integer modulo m with the property that the line segment between the vertices I and j is an edge in Pn if and only if the line segment between phi I and phi j is an edge of Pn. Okay, so the n-dihedral group is the set Dn with the binary operation of function composition, right? So we justify calling that as a group, okay, with theorem 417. Okay, so how do we show that this theorem is this dihedral group is a group? Okay, it's given in theorem 4.7. Okay, so you can read the proof down there. Okay, the proof down there. So you can see the which is the how the line segment and not line segment are mapped. Okay, and then which is the identity. The identity is the same identity where iota k will map to k, right? And then the inverse. Okay, the inverse is like what you see in a permutation group. Okay, so if you look back at this triangle, for example, the first one here, the triangle down here, okay, how it form a dihedral group. Okay, it's all the mapping that map this integer modulo n. For this example, the vertices are 0, 1, and 2. Okay, so 0, 1, and 2 are the vertices. So look at it as elements in integer modulo 3. Integer modulo 3 has 3 elements as well. But now, not necessarily D3 will isomorphic to integer modulo 3. It is not that way, right? So we look at the dihedral group as one-to-one function that map onto integer modulo n. For this case, integer modulo 3. Okay, so how many one-to-one mapping and onto that you can create? Okay, so for example, I can start my mapping with my first mapping. For example, I want to have 0 map to 0. So 0 to 0, 0 is not an edge of Pn. Okay, so now this is a polynomial degree 3, so this is P3, right? So that's my mapping 0 to 0, and then 1 I map it to 1, 2 I map it to 2. So this is one of the element in D3. Okay, so I can have D3. Okay, so I can have one of the element is 0 to 0, 1 to 1, 2 to 2, because 0 to 0 is not an edge, 1 to 1 is also not an edge, and then 2 to 2 is also not an edge. So I can have an iota there, right? Okay, that's one of the mapping. Okay, so another one. So let's say that I want to map 0 to 1, okay, and then 1 to 2, 2 to 0. Okay, because 0 to 1 is an edge, 1 to 2 is also an edge, 2 to 0 is also an edge. Okay, so I can have another one to one and onto mapping there, where 1 map to 2, 2 map to 3, 3 maps to 1. All right. Okay, that's another mapping. And then I can have another mapping. For example, I want to have 0 map to 2, 2 map to 1, 1 map to 0. That is also another mapping that is 1 to 1 and onto. Okay, so I can have another mapping there. I have, what was it just now, 0 to 2. Okay, and then 2 to 1, 1 to 0. Okay, let me make This is a correction there. Okay, that was 0 to 1, 0 to 1, 1 to 2 just now. Okay, so I have up to now I have three 1 to 1 and on 2 mapping. Okay, so if I go on, okay, if I go on, I can have another three more 1 to 1 and on 2 mapping. Okay, 1 to 1 and on 2 mapping. Mm, so we have a look at it in the in the next theorem. All right. So that's how the one-to-one and onto mapping is constructed. Okay. We are not going to do it one by one. So we are going to do it by help of some theorem. Okay. So theorem 417 is showing that it will form a group. There will be some more elements in here in D3. Okay. I'm not completing it there. Okay, because we're going to look at it by an example. Okay, look at example 418 down here. It's read together with figure 419. So see that for n greater or equal to 3, of course, our n always greater or equal to 3 in order for us to form an n-gon. Okay, and then rho here is a mapping from integer modulo n to integer modulo n given by rotating the n-gon. Okay, the n-gon Pn by 2 pi over n, which just rotates each vertex to the next one. Okay, I mean that the first one, 0 will map to 1, 1 will map to 2, 2 will map to 3, 3 to 4, 4 to 0. Okay, that will rotate each point by 2 pi over n only. Okay, so we name this mapping as rho, and then rho means rho of k equal to k plus 1 under addition modulo n. Okay, so depending on what n we are doing. For this example, if we look at this figure for 19, we're looking at D5. Okay, our n is 5. Okay, our n 5 because we have 5 vertices, right? Okay, so obviously in integer modulo 5, you have 5 elements, 0, 1, 2, 3, and 4, right? So that the function rho match edges to edges, and it is one to one and onto. So rho is a member of nth root of unity. Okay, so rho is a member of nth root of unity. And then the second element is the reflection about the x-axis. Okay, about the x-axis, which we call as mu. Okay, so we look at the same figure, but now we see the glance of x axis. Okay, x axis there. Okay, the axis down, the axis there, right? So we see that in D5, mu of 0 is 0 itself, because on that axis, the reflection of 0 is on itself. Okay, the reflection of 1 will go to 4. 4 will reflect to 1. Right? 4 will reflect to 1, and then 1 will reflect to 4. 2 will reflect to 3. 3 reflects to 2. Okay, so that's what it says here. Okay, so then in general, if k is any element in integer modulo n, then mu of k will always give you the negative of k. Okay, so be careful, the negative of k means the additive inverse of k. Okay, so recall that in integer modulo k, minus k is the additive inverse of k, which is n minus k for k greater or equal to 0, and minus 0 is 0, means that the additive inverse for 0 is 0. Okay, so if you can see back in integer modulo 5 just now, we know that inverse for 1 is 4, inverse for 4 is 1. Okay, that's why we see that 1 maps to 4, 4 maps to 1. Okay, same goes for 2 and 3. Okay, additive inverse for 2 is 3, and additive inverse for 3 is 2. That's why they map each other under the permutation ataupun under the mapping of mu. Okay, and then those are the two. Okay, the first two mapping that we could get in any n dihedral group. Okay, so now let us check if mu rho equal to rho mu. Okay, so you can see that by checking each function, what each function does to 0. Okay, so you can see that if I perform mu row 0, so because row 0, okay, row 0 just now map to 1. Okay, this one, this mapping. Okay, so row 0 become 1, and then mu of 1, under mu, 1 maps to 4. Okay, ataupun in general, it is n minus 1. Okay, in integer modulo 5, it is n minus 1. So you always get n minus 1 for mu row of 0. Okay, and then by the same experimentation, if you do row mu of 0, so because mu of 0 maps to 0, and then row 0 maps to 1. So row mu of 0 for any n will always map to 1. Okay, so since n greater or equal to 3, n minus 1 not equal to 1. Okay, so which implies that mu row will not equal to row mu at any n. Okay, therefore, for all n greater or equal to 3, Dn is not abelian. So n dihedral group is an example of a non-abelian group. It's a good example of a non-abelian group. Okay, so that's why n dihedral group is a very important example for n dihedral or a non-abelian group. Okay, on top of group of permutation. Okay, so look at the theorem. We want to know how many elements are there in n dihedral group, right? Because it seems like we have rotation and reflection, but when do we stop? Okay, so the theorem says that the order of the dihedral group Dn is 2n. Okay, it's always 2n. Means that for if we look at the previous example, for pentagon, you're going to have D5. So element of D5, you're going to have 10 elements. Means that 10 permutations that you can get. Right? If you look back at the triangle on top, means that you're looking at D3. So D3 will have 6 elements. That's why I said just now. I listed 3 of the permutation. We're going to have another 3 of the permutations, okay, for your practice, right? All right, so that's the theorem. Okay, the proof is given down there for you to read. However, how do we recognize, okay, or list down the the 2n elements of Dn is by using this relation, right? So Dn, okay, so Dn is equal to the set, okay, the set containing all these permutations. So what are the permutations? First, you must have the iota, of course, okay, the iota, or row to the power of 0 just now, okay, not moving any elements to any other vertex, right? And then you have row, okay, and then you have row square. Row square means that if just now you have row as 0 mapped to 1, so row square means that perform row another one more time, means that 0 to 1, and then 1 will map to 2, like that, and then 2 will map to 4, 4 will map to 1, 1 will map to 3, 3 will map to 0, and then you stop. Okay, because next one 0 will map to 2 again. Okay, so that is row to the power of 2. Okay, and then row to the power of 3, do the same thing. Okay, do the same thing means that now it's 3 times, means that 0 will map to tadi tu akan pergi jauh sikit depan ketiga. Okay, and so on. So you're gonna have row cube. So when do we stop? We stop at n minus 1. Okay, means that if you are doing your work in D5, so your rotation will stop at row 4. Okay, you only rotate row 4 times, because at 5th time it will be the same with iota balik semula. You go back to the iota, the identity permutation, right? So you stop at n minus 1, and then that will give you the first n elements of Dn. Okay, means that for example, if I work with pentagon with D5, so the first all the rows that I'm doing together with the iota will give you the first 5 of the permutations. And then what are the other 5? Because we know that in pentagon we have 10 permutation. So the other 5 is simply by multiplying mu in front of each what you get in the first 5. It means that mu multiplied with iota will give you mu, and then mu multiplied with rho will give you mu rho, right? And then mu multiplied with rho square will give you mu rho square, and so on. Last kali tadi, the final one was rho power of n minus 1. So, of course, the n will be mu rho to the power of n minus 1. Okay, so that's how you construct all the 2n elements of Dn. Okay, for example, just now, if you work with D5, you're going to have 10 elements. Okay, what are the elements? The iota, rho to the power of 2, to the power of 3, to the power of 4. Stop. Okay, we have the first 5. And then, what are the other 5? You multiply all these 5 that you get from the first one with mu in front. Okay, with mu in front. Okay, so if I look back at my triangle in the beginning of the story just now, okay, so I have iota, okay, so this one is my rho, okay, so this one is my rho square, and then I stop there, okay, because I work with D3, so I need to stop at rho to the power of 3 minus 1, which is rho to the power of 2, right? The next one, I need to have my mu rho, sorry, my mu only, okay, mu multiply iota. So that's one will give, I need my mu iota, okay? So here I'm going to have my mu, and then I have my mu rho, and then I have my mu rho square. And then my set is complete for D3. Okay, so if I rewrite it carefully, I will get D3 is equal to iota rho square mu mu rho, and then mu rho square. Okay, and then if you want to examine further what are mu, what are, because you know that rho is 0, 1, 2, and rho square is 0, 2, 1. You may want to know what is mu. So mu is again just now reflection about the x-axis. So mu, you draw the x-axis there, right? So you can see that mu is 0 will map to 0, 1 maps to 2, and then 2 maps to 1. So that is your mu. Okay, so that's your mu. Okay, so mu is that, and then mu rho, you just multiply 1, 2 with 0, 1, 2, and then mu rho square, you multiply mu with 0, 2, 1. And then your D3 is complete. All right, so that's how you interpret n-dihedral group. So you can practice with any value of n. Okay, so that's all for this video. Thank you very much.